Parker Solar Probe made history by becoming the first ever spacecraft to venture into the Sun's corona. The heat in this region of the Sun's atmosphere reaches a mind-boggling million degrees Celsius. But don't worry, this amazing spacecraft was equipped with some seriously cool technology. From its heat shield made of carbon composite foam to its innovative cooling system, the Parker Solar Probe was able not only to survive, but make history as the first ever spacecraft to touch the Sun. Get ready to be amazed as we dive into the engineering behind this incredible mission. Launched in 2018, the Solar Parker Probe is a powerhouse of technology, with the goal of getting up close and personal with the Sun. How close, you ask? Well, it's set to come within 9.86 solar radii from the center of the Sun. That's only 6.9 million kilometers away, or 4.3 million miles. This mission is a hot one, with speeds reaching up to 690,000 kilometers per hour, which is the equivalent to 0.064% of the speed of light. Yes, you heard that right. The Parker Solar Probe is the fastest object ever built. But what makes this mission even cooler is the fact that it is NASA's first spacecraft named after a living person. The spacecraft is named after the Nigerian physicist Eugene Newman Parker, who is a professor emeritus at the University of Chicago. The mission has been a long time coming, with its roots tracing back to 1958. But because of financial constraints, it kept getting pushed back. Fast forward to 2018, and after a major overhaul, the Parker Solar Probe was finally launched and made history on October 29, 2018, when it achieved the closest approach ever made by an artificial object to the Sun. That's right, the Parker Solar Probe broke the previous record of 42.73 million kilometers set by the Helios 2 spacecraft, way back in April of 1976. Also, Parker Solar Probe began its 14th close encounter with the Sun on December 6, 2022. This encounter marked the 14th of 24 planned close approaches to the Sun, with the ultimate goal of coming within 5.3 million miles of the solar surface. The spacecraft traveled at a speed of 364,639 miles per hour during its closest approach, also known as perihelion. The perihelion is the point in a planet's orbit where it's closest to the Sun. It's a Greek word that literally means around the Sun. On the other hand, aphelion is the point where an orbiting body is farthest from the Sun. During its previous close encounter with the Sun on September 5, 2022, the spacecraft flew through one of the most powerful coronal mass ejections in recorded history. With the Sun's activity increasing as it approaches its solar maximum, scientists expect Parker to encounter even more exciting phenomena in the coming close approaches. Dr. Noor Raufi, Parker Solar Probe project scientist at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, said that every close encounter opens up new opportunities to understand better how the Sun works and how it affects us here on Earth and beyond. To provide a comprehensive view of the encounter, the European Space Agency's Solar Orbiter, NASA's Solar Terrestrial Relations Observatory A, and radar telescopes on Earth view the Sun from the same angle as Parker at the beginning of the encounter, and then slowly progress toward a 90-degree angle from Parker. Similarly, the ESA's Bepi-Colombo mission will start viewing the Sun from the same angle as Parker, and progress towards observing it from a 90-degree angle from Parker on the outbound side of the encounter. But the real question is, how did the Parker Solar Probe not melt when it entered into the corona and touched the Sun? The answer lies in the corona itself. The corona is a fascinating and mysterious part of the Sun that has intrigued scientists for centuries. It is the outermost layer of the Sun's atmosphere, consisting of plasma and extending millions of kilometers into space. Despite being so far from the Sun's surface, the corona has temperatures that are much higher than those of the Sun's surface, a fact that has puzzled scientists for a very long time. This is because the laws of thermodynamics tell us that heat cannot flow from a cold body to a hotter one. The Parker Solar Probe was designed to help solve this mystery by studying the corona and uncovering its secrets. One important aspect of the probe's mission is to understand the concept of heat versus temperature. While temperature measures how fast particles are moving, heat represents the total energy these particles can transfer. The corona is able to maintain its high temperatures despite having low particle density, because the particles in the corona are highly energetic and are constantly moving and colliding with one another. Heat transfer occurs when energy is transferred from one particle to another due to the collision of particles. The temperature of a body is measured of the average energy of its particles. So the more energetic the particles, the higher the temperature. In the corona, the particles are highly energetic and constantly colliding with each other, transferring energy from one particle to another. Despite the low particle density, the high energy of the particles means that the corona is able to maintain its high temperature. The Parker Solar Probe is equipped with a thermal protection system, or simply TPS, to keep it safe from melting. The TPS consists of a heat shield made of carbon composite foam sandwiched between two carbon plates. Despite being only 4.5 inches thick, the heat shield can withstand up to 1650 degrees Celsius, allowing the spacecraft to maintain a temperature of 30 degrees Celsius. The edges of the heat shield are equipped with 7 smart sensors that detect any direct sunlight and alert the central computer to direct the spacecraft to correct its position. This allows the spacecraft to remain protected from the sun's intense heat and radiation, ensuring its longevity and the success of its mission. The team also took special measures with the wiring, using sapphire crystal tubes to suspend it, and using niobium wires with a high melting point of 2,470 degrees Celsius. To ensure that the spacecraft remains safe, it is equipped with 4 light sensors that can detect the first traces of direct sunlight and engage movements from reaction wheels to reposition the spacecraft within the shadow yet again. With radio communication with Earth taking about 8 minutes in each direction, the Parker Solar Probe must act autonomously and rapidly to protect itself. According to project scientist Nikki Fox, the team describes it as the most autonomous spacecraft that has ever flown. If the shield were not between the spacecraft and the sun, the probe would be damaged and become inoperative within tens of seconds. Not only is the Parker Solar Probe studying the sun, it is also powered by it. The spacecraft has a dual system of solar panels, known as photovoltaic arrays, which harness the sun's energy to provide power to the spacecraft. One of the arrays is used when the spacecraft is outside 0.25 astronomical units from the sun, while a smaller array is used when the spacecraft is closest to the sun. As the probe gets closer to the sun, the intensity of solar radiation increases, making it necessary to protect the solar panels from overheating. To prevent overheating, the Parker Solar Probe is equipped with a unique cooling system that circulates a small amount of water through its solar arrays. The water absorbs heat as it passes behind the arrays and then releases it into space through the spacecraft's radiator. This allows the solar panels to remain at a safe operating temperature, even as the probe approaches the sun. The Parker Solar Probe is on its way to gather a wealth of information about the sun and its corona. By the end of its mission, the probe will send data from within 6.16 million kilometers of the sun's surface, revealing solar secrets at depths that have never been reached before. We hope you enjoyed this video. Make sure to subscribe, like the video, and watch these ones as well.